So today is ice and rain control. Yay, I know you're really jazzed up about it. Negative effects of icing. Well, I can't think of any positive effects. It increases drag. First of all, if ice sticks to the airfoil, it changes the shape of that airfoil, and so now it is not creating lift for the same amount of drag. You're going to have to go to a higher angle of attack when ice forms on the wing in order to get the same amount of lift, because the ice on the wing is going to mess up the aerodynamics. So you're going to have to go to a higher angle of attack. What's going to happen to the induced drag if you go to a higher angle of attack? It's going to go up. Okay. If ice sticks to somewhere on the airframe and just causes parasitic drag, does that cause drag?
Yes.
Yes, very good. That's right. Parasitic drag is drag. What? Also, if you stick ice to the airplane anywhere, the gross weight of the airplane increases. And if the gross weight of the airplane increases, to maintain the same altitude, you're going to have to go to a higher angle of attack even more than you did before, and induced drag will go up for another reason, because the airplane is at a higher gross weight. So these are all negative effects of having airframe ice. Now, if you get ice on the intake of your jet engine, and you get a whole bunch of it, you won't be able to get as much air into the engine, and jet engines are dependent upon the air going through it to be able to produce thrust, because you've got to be able to burn that air. So if you restrict the intake of a jet engine, it will develop less thrust. Even if you don't have icing on your filter or your air intake on a piston engine, if you get ice on your propeller, the airfoil on that propeller is going to be less efficient, and you're going to have to burn more horsepower, or burn more fuel rather. Well, let's see, I guess you'd have to develop more horsepower and give it to the propeller shaft, because the blades are going to have to go to a higher angle of attack to get the same amount of thrust, just like you'd have to go to a higher angle of attack on your airfoil to get the same amount of lift if there was ice on the airfoil and the ice was messing up your aerodynamics. So in general, ice on your power plant is also going to have negative effect. Ooh, what if you were a turboprop and you had ice in the intake and you had ice on the propeller? Ah! That's what you would say. You would say, ah! So, types of ice protection systems. There's anti-icing systems and there are de-icing systems. Anti-icing systems are there to keep the ice from sticking to the aircraft in the first place. In theory, if you have an anti-icing system and it is working well, ice will not stick to the portion of the aircraft that it's anti-icing. For instance, on transport category jets, they typically take hot bleed air off of the compressor of the engine and they route it to the leading edges of the wings. The wings' leading edges stay hot enough, that is, they stay above the freezing point of water, so if ice attempts to stick to it, it'll melt immediately and it won't stick. So it's an anti-icing system. A de-icing system is a system that is designed to allow the ice to form first, and then it gets rid of the ice after it's already formed. In particular, the most likely case of this would be rubber baby buggy bumpers, that is, pneumatic de-icing boots. The rubber de-icing boots typically found on airfoils on small to medium-sized aircraft, where the boots inflate. Typically, you wait until the ice forms and then inflate them so the ice will crack and then leave the aircraft. Those are designed to be anti-icing, in that the way it's supposed to work is you wait till the ice forms and then it gets rid of the ice. However, some of these systems, although they're designed as a de-icing system, it may work as an anti-icing system, and some of the anti-icing systems may work as a de-icing system, and it's important as a pilot to know if you can use an anti-icing system as a de-icer in case you get into that situation. So as we go through these systems, I'm going to tell you, well, this one is designed as an anti-icing system, but it will or will not work well as a de-icing system, and vice versa. This is, of course, my favorite, the airframe bleed air anti-icing system. It takes bleed air off of the engine, off of a turbine engine. That's off of the compressor. It's pressurized and it's hot. And you route it, like I said, to the leading edges of the wings and the vertical and horizontal stabilizers, and you keep them nice and hot. For instance, I have a diagram here of a 727. Let's see if I can focus it very well. And it takes bleed air off of the compressors of the engine, and this is the main pneumatic system that's there to start the engines because it has pneumatic starters, and it routes this hot air towards the leading edges of the wings. It doesn't show the air routed to the tail. And here's what it looks like. Here's a cross section. There's just a hot air duct running down the leading edge of the wing, and there's a skin on the inside about 1/2 of an inch or so, and this hot air is held between the outside skin and the inside skin. It ends up going overboard, and this air is nice and hot. And so any ice that tries to stick will melt immediately, so it won't stick at all. This is a very, very good system. Of course, the disadvantage is that it takes power off of the engine. If you look in the flight manual, it says if you run the airframe anti-icing system, you have to, fuel burn goes up, say, 2% or something like that. If you maintain the same thrust on the engine, you'd have to push the throttle forward just a little tiny bit. So you would have to take this into account if you were going to fly through icing conditions. Now, the good side about this air is that it's really stinking hot, and so it melts ice really well. The downside is it's really stinking hot. For instance, it could be 500 to 800 degrees Fahrenheit. Woohoo! Yeah, deity, insert deity's name here, that's correct. The downside is that this leading edge of the wing here is made out of aluminum. Aluminum melts, I mean liquid, at 1100 degrees Fahrenheit. If you heat it up more than about halfway up there, 600 or 700 degrees Fahrenheit, you're going to start destroying the strength of the aluminum. It won't melt at 700 degrees Fahrenheit, but its strength will be dramatically reduced. So on airframe, bleed air, anti-icing systems, one of two things is going to occur on the ground. Either A, you will be restricted and you cannot use the airframe bleed air anti-icing system on the ground, or it has some type of temperature regulating system so that it won't let the air go in there if it's really, really stinking hot and will damage the leading edge. Now you got to remember, this system is designed to work in flight, say at 36,000 feet. Standard day temperature at 36,000 feet and higher is minus 56 Celsius. So you're flying along at 500 knots true airspeed. You think that air blowing past the leading edge of the wing will pull a lot of heat energy off of it? Yeah, it'll pull a lot. So in order to combat that and keep the temperature of the skin above freezing, it needs to be really, really hot. But if you're on the ground and the forward airspeed is, say, 1 knot, you're not going to have all that cold air, and it's not going to be minus 56, and unless you're in North Dakota in the middle of the winter. Has anybody ever seen minus 56 Celsius? Yeah, it's pretty stinking. You saw it, huh? It was on TV, or you walked outside in it. Yeah, did you have any parts freeze off? Yeah, me neither. In any case, you still wouldn't have 500 knot true airspeed wind blowing past you, so it wouldn't take the heat energy off. So be careful when you operate these aircraft, and you're going to find them on transport category jets, big biz jets, big turboprops. Make sure you understand what the ground restrictions are. Anybody not know where the hot air comes from? And don't write down Mr. Johnson. That's an accurate statement, but Mr. Johnson doesn't provide hot air for airframe, bleed air, anti-icing systems. Although in an emergency, I've had a daydream one time. Does anybody in here have a lot of hot air? I have a lot of hot air. I'm an Embry-Riddle instructor. Dun, dun, dun. Oh, sorry, never mind. Okay, now you can get the same engine power. You're just going to have to push the power lever up a little more. But now your fuel flow is going to be higher. Now here's an interesting thought. Has anybody ever heard of FAR Part 91? No. Not very many of you. Well, in FAR Part 91, and it talks about it in FAR Part 121, you have to plan on how much fuel you're going to take with you. Even under Part 91, you got to have enough fuel to get where you're going, and if it's IFR, you got to have 30 more minutes than that, right? And then if you got an alternate, you got to be able to fly your alternate as well. Okay, guess what? If 45? Okay, fine. 45 minutes. See if I care. Okay, you're going to get that. Yeah, so much for your extra credit project. Yeah, that's right. Day VFR is 30 minutes, and night and IFR for airplanes is 45. And that's the same, plus having to go to your alternate. And that's the same Part 91 or Part 121, by the way. In any case, you have to take into account weather. You have to take into account anything that's going to increase your fuel flow. If you look at the weather and it says you're going to fly through forecast icing, Do you need to put the fuel on board in order to be able to run your airframe anti-icing system? Yeah. Well, wait, can't you burn it out of that 45 minutes reserve? You got 45 minutes. Isn't it legal, moral, and ethical to do that? To plan on burning your reserve? No, wait a minute, it's in reserve. If you know you're going to burn it before you take off, it's not the reserve anymore. So you cannot use your reserve to say, if I run into some icing, I'll use my reserve. Whether it's forecast icing or known icing, in either case, you're expected to be in the icing conditions, and you are expecting to have to run your airframe bleed air, and of course if you had an engine bleed air, you're going to have to run your anti-icing systems. And if that affects your fuel flow, you've got to put that fuel on board the airplane prior to takeoff, whether it's Part 91 or whether it's Part 121. And I already told you about on this system here, although it's designed as a de-icing system, in flight it works well as a de-icer. If you get into icing conditions and you look out the windows and you go, oh, poop. Look at the icing conditions. Yes, if you turn it on, it'll de-ice that portion of the wings and stabilizers that gets heat. And that's where the ice sticks. If you didn't know about ice tends to stick first to the smallest radius items. For instance, antenna have a small radius. The ice will stick there first. The tail has a smaller, the leading edge of the vertical and horizontal stabilizer have a smaller radius curve on the leading edge than the main wing. So if you look out on the main wing and you see icing, guess what the icing's like on the tail? Worse. Think about that for a minute. If you see icing on the wing, it's worse on the tail. Airframe electrical anti-icing. It's just a heating element. One of the two things that happens when you run electricity through a wire is the wire gets hot. If you run enough electricity through it, hey, somebody's hitting the clicker somewhere. If you run enough electricity through it, it'll get good and hot. That's what a pitot heat is. Pitot-static port, or pitot heat, is just an electrical coil of wire that you run electricity through it. Now, if you stuck a compass next to it when it was on, I think it would affect the compass because it's also going to have lines of flux. So you've already operated an electric anti-icing system for the airframe. Now, that pitot heat, guess what? It's hot enough, it'll work okay as a de-icer. If you're flying along and it gets iced up and you go, again, you can turn the pitot heat on and it should de-ice it. Now, you want to check the operation of pitot tubes, and when you start flying an airplane that can go into known icing conditions, you're also going to have heated static ports. The best way to check if it's really working well is not to wrap your lips around it and see if your skin on your lips come off. And it's not even to touch it with your hand. It's look at the ammeter. If, for instance, you look at the circuit breaker for the pitot heat, and you look at that circuit breaker, and it says 20 amps on it. How many amps do you think it's going to use under normal operations and when you turn it on? Yeah, times 0.7 is about 14 amps. So you ought to be able to look on your ammeter in the airplane. If there's 0 and there's minus 30, and it's sitting here at like minus 2 because the current coordinator's on a 172 during pre-flight. When you turn this on, it ought to go 14 amps more to the negative. Or if you're in an airplane that has this is for a battery circuit ammeter. If you're in an airplane that has a generator circuit ammeter, and it's 0's down here and say 100 is up there, if it's sitting here at about 20 and you turn this on, it ought to go up to about 34 amps. That's the best way to check to see if your electric anti-icing system is working. Heated windshields. Now, if you fly an airplane that's pressurized and it's got glass windshields, glass is rather brittle, and the colder it gets, the more brittle it is. So you're going to want to have the heat on all the time. Essentially, your pre-takeoff checklist is going to say turn on the windshield heat, and your post-landing checklist is going to say turn off the windshield heat. And it doesn't matter whether you're in icing conditions or not, it keeps the window from cracking at those high temperature, or high altitude slash, well, not because of altitude, but because where you fly, it'll be at a low temperature. Of course, now the byproduct of keeping it heated all the time is it's not going to ice up. Yay! Question?
Other windshields also heated except this glass?
Well, there's other heated windshields, but the glass ones are the ones that you're worried about cracking, even if it's not icing. So if it's a glass windshield, you're going to turn the heat on just prior to takeoff, and you're going to leave the heat on until after you land. Now, there are a few airplanes with leading edges that have electric anti-icing systems. For instance, small twin jets, for instance, like a Cessna. Got a couple of engines back here. It's got straight wings. Thanks. I know. Here's your small Cessna. Woohoo! Yeah. Okay. They're turbofans. Are you happy? And this outer portion of the wing right here they're pneumatic boots. They inflate and deflate. But right in here, it's electric. Now the electric, if you ran the electric anti-icing all the way out, the whole leading edge of the wing, it would take a lot of electricity. You'd need a bigger generator on board the airplane. The empty weight of the airplane would go up, and it would burn a significant amount of fuel to run this generator. So they only make part of it pneumatic. Why don't they make all of it pneumatic?
They don't want big chunks of ice falling to the engine.
Yeah, very good, Patrick. They don't want big chunks of ice. The pneumatic system is de-ice. If we ran it all the way to the leading edge of the wing and then let the ice form and then turn it on, the ice would crack when we turned it on and get sucked into the engine, and we'd have foreign object damage on the engine. So there are some leading edges of wings that have electric, and it's anti-ice. So as soon as you think you're going to get into icing conditions, you're going to turn this on prior, because you totally, although it would work as a de-icing system, you don't want it to be de-icing. You want to turn it on before the icing hits, so that no ice will stick, so that so no ice will end up going into the intake of the engine. So although in all cases here, electric anti-icing for the airframe is designed as an anti-icing system, they will de-ice if the ice forms first, and then you turn it on. Although in all these cases, you're going to want to turn it on prior to the ice forming, if at all possible. In particular, if turning it on would cause ice to go into the engine. All right, my personal favorite, chemical anti-icing. I remember back in the old days when I was younger, it was back in the 70s when the green things started occurring. You know, no, let's not pollute and stuff like that. So DuPont, I think it was a chemical company, and they were caught polluting and stuff. So they spent money, this is America, on a marketing campaign with TV advertisements, and it would say something like, life would not be possible without chemicals. Which is an accurate statement, although it would also be easier without, pollution. And when I remember years later thinking of that advertising and going, yeah, life would not be possible without chemicals, but it's sure a lot more fun with pharmaceuticals. Chemical anti-icing. There are two different chemicals that are typically found on airplanes that might be used for anti-icing. One of them is isopropyl alcohol, and the other is ethylene glycol. If you go to a grocery store or a department store and you buy rubbing alcohol, it's 30% water and 70% isopropyl alcohol. The reason they put the water in it is so it's less flammable. Isopropyl alcohol is not for drinking. Do not drink isopropyl alcohol. If you use isopropyl alcohol in an airplane for anti-icing, it's going to be used at 100%. But hey, who cares if it's flammable? The gasoline is flammable. And so if you if you drink an Everclear shots in the cabin, that's flammable too. So if you do that, make sure you don't do Everclear shots during an electrical fire. I don't know anyone that does Everclear shots. To answer your question. Ethylene glycol is the same ingredient found in automotive antifreeze. Wow, so you may have seen ethylene glycol as well. Now, where are you going to find chemical anti-icing? Essentially, three places. The alcohol is typically used on alcohol props and alcohol windshields. The disadvantage of alcohol props and alcohol windshields is that this system only works as an anti-icer. That is, if the ice sticks and then you squirt the alcohol on it, it will not get rid of the ice. This alcohol is in a tank in the airplane, and it is not heated, and so it will not melt that ice. It won't let any ice stick to the ice that's already formed, but you may already be screwed. Question?
Is the glycol like a slippery kind of?
It's kind of slippery, yeah. It's not really good as a lubricant, but it has some viscosity. It has viscousness. And yes, viscousness is a word. I looked it up in the 1959 Webster's Intercollegiate Dictionary. Okay, let's all say viscousness on the count of three. 1, 2, 3. Viscousness. Very good. And those of you at home, go ahead and pause and say it a few times as well. Same thing for alcohol windshields. If you wait till the ice forms on your windshield and then you turn on the alcohol, it won't get rid of any ice that's already there. It'll just keep ice from sticking to the ice that's already there. So what you've got to do with alcohol props and alcohol windshields is that before you think you're in icing conditions, you've got to turn the system on, and you can turn it on low. You get it's like a volume control knob, and it changes how many amps go to the pump. You turn it on low, and as soon as you're in icing conditions and you go, then you turn it on high. Now that's one of the disadvantages, is that it doesn't de-ice. The other disadvantage is that there's a limited quantity of alcohol on board the airplane, isopropyl alcohol that is, and when you run out of fluid, you're hosed. So if you get into icing conditions, you really need to leave as soon as possible. Also, there is a system, the vernacular in the industry is weeping wings. You can buy it, I think, on a brand new Mooney airplane, and they actually have little tiny holes in the leading edge of the wing. Darn, I don't have any green, so I'll just have to use red. It actually comes through little tiny holes, and the fluid gets blown back by the slipstream. And it actually works really, really well because it doesn't cover up just the leading edge of the wing, but the ethylene glycol. Just so you know, weeping wings don't use alcohol. Weeping wings is where you would use the ethylene glycol. It gets the airflow pushes it back across the surface of the wing, so it doesn't just anti-ice the leading edge, it also anti-ices the rest of the wing. But again, it's not heated, so it is not a de-icer. It will not de-ice. So before you think you're in icing conditions, you're going to turn this on low, and when you get into icing conditions, you're going to turn it on high, and again, limited fluid, you're going to want to get out of your icing conditions, as soon as possible. So there, in either case, whether it's alcohol props, alcohol windshields, or weeping wings, it only works as an anti-icing system, not as a de-icing system. Jason?
What type of aircraft have alcohol props?
Oh, okay, good point. What kind of aircraft have alcohol props? Typically older aircraft. No one is making older piston-powered aircraft. No one is making alcohol prop airplanes anymore. However, you may get that job. You know, those of you that don't want to be a flight instructor right out of school, you might be able to get that job flying that 1955 Beechcraft Baron, between Flagstaff and Albuquerque through thunderstorms, and it'll be certified for known icing conditions, and it'll have alcohol freaking props on it and an alcohol windshield. So you might just fly one of these things. Did you have a question, Stephen?
They're going to shoot out like up the propeller like a weeping wing?
Yeah, the question is the propeller like a weeping wing? The answer is no. This is the best picture, a canned picture I have on me. And essentially the answer is no. What does occur is that this blade right here, it has a rubber boot on it, and on that boot it has grooves. So the centrifugal force flings it outward towards the tip of the blade, and the grooves on the first third only help keep it going outward instead of going along the cord or 90 degrees to the something or other on a propeller. Yeah, let's put it this way. Let me rephrase that. The alcohol gets squirted out right here, and it goes down these grooves and some of it comes off. You don't get as much icing on the tips because you're spinning fast, and things don't stick very well when you're spinning around at 600 miles an hour. Did you have a question, Jacob?
Yeah. Does the alcohol evaporate?
The alcohol evaporate? It's cold, man. Besides, it only has to stay there for a few seconds. Any given molecule of alcohol is only going to be on the blade for a few seconds. Besides, most of the alcohol I come in contact with, I drink it before it evaporates. Wing de-icing boots. Wing de-icing boots. They are powered by pneumatic power. That is, it's either an air compressor driven off of the engine, kind of like a vacuum pump except in reverse, or it's off of bleed air off of the compressor of a turbine engine. The boots operate either for a certain amount of time and then they stop if they have a timer on it, or on some systems the pilot has to turn them off. Essentially, rubber boots are set up on the leading edge of a wing, and there's a boot here, and 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 a boot here. And every other one inflates. This one will inflate, and this one will inflate, and this one will inflate, this one will inflate. And then these will be deflated and pumped down so that they're flat again. And then when that occurs, then the opposite happens. Then this one is flat, this one is pumped up, this one is flat, this one is pumped up, this one is flat, this one is pumped up, this one is flat, and this one is pumped up. And the ice cracks. You have to wait until the ice cracks. If you turn this on too soon, then the ice will end up forming around the maximum inflation area of where these are, and then of course you can think about the lack of laminar flow. It's going to be really turbulent, and you're going to have tons and tons of drag. These boots are typically run along the length of the leading edge of the wing. Once you get the ice cracked and the wind blows, the relative wind blows the ice off, you have to turn off the boots and wait for the ice to form again. So it may run it for about a minute, and then after the ice is gone, you wait for a few minutes and wait for the ice to build back up, and then you've got to turn it back on again. We're going to use 1970, pre-1970, before 1970, and after or post-1970 as a cutoff. It's pretty generic, but it'll work for the test. Pneumatic de-icing boots on airplanes built prior to 1970, the boots inflate slowly and deflate slowly. So they only work as a de-icing system. You've got to wait until the ice forms and then turn on the boots so the ice will crack. If it's a post-1970 set of pneumatic wing de-icing boots, the system generally, post-1970, the boots inflate and deflate very, very rapidly, and it'll break off the ice as it's forming, so you don't have to wait until the ice forms. Now, that's typically the way you want to do it, but if you happen to leave the old-style boots on, inadvertently, you're going to get ice forming around the outside deflation area, and it's going to not end up cracking. On the newer systems, if you happen to leave it on, it would still anti-ice. So for test purposes, if it's the old pre-1970 pneumatic wing de-icing boots, they are de-ice only, and you have to wait till the ice forms. If they're post-1970, the boots operate fast enough that it'll crack the ice as it's forming, and although it's best as a de-icer, it will work as an anti-icer. Electric propeller de-icing is also known by the term hot props, because the propellers get hot. Literally, there's heating elements on the propeller blades. Let's just say, for instance, that we have a couple of propellers. And let's say it's on our twin-engine airplane. and there's the spinner, and here's our propeller blades. And the boot is going to, on each of these propeller blades, is going to go out about a third of the way or so. And inside of each boot is going to be a heating element. If we look at this heating element this boot really big, we're going to see two heating elements. And we're going to have the plus side for one heating element and the plus side for the other. So there's going to be two heating elements in each boot. If we turned on the propeller anti-icing, there's going to be an ammeter for each propeller. In fact, it's probably going to say propeller on it somewhere. And let's just say that that's 0, and up here is 50. We'll say that that's 0, and up here is 50. When we turn this system on, one of the propellers is going to come on. Let's say that we turn it on, we're going to see this ammeter, say, go up to 30 amps. The inside heating element is here's going to be on, here's going to be on, and there is going to be on. And it'll go up there for about 30 seconds. Then it'll come down to 0 for a second or two, and then it'll come back to 30, because now instead of sending electricity to the inside, it's sending electricity to the outside. So now the outside heating element's going to get hot. And it'll stay there for about 30 seconds, and then it'll go to 0. Then if you're watching these gauges, the other propeller ammeter will come up to about 30, and the inboard ones will get hot for about 30 seconds. It'll go down to 0 for a second or two, and it'll come back to 30, and then the outboard heating elements will get hot. And then after it's done that for 30 seconds, it'll go down to 0, and then the other propeller will start all over again. So it takes about 2 minutes for this cycle to occur. Now, the nice thing about this system is even though it's called de-icing, it does work well as an anti-icing system. So you can turn it on and leave it on, and ice won't build up. I already showed you the timed operation, and the best way to check to see if this system is working is similar to that of the pitot-static heating, is turn it on. You'll probably have the engines running by then, but you're going to check for that cycle to see if the appropriate amps come up on each one. For instance, if you turned it on and on this propeller right here it ran good, it went up to 30, down to 0, went up to 30, over here went to 0, up to 30, came down, and the next time it only came up to 20 amps, it probably means that one of these three heating elements is not working correctly. So if this one, for instance, doesn't get hot, then when it de-ices, it's not going to de-ice symmetrically, and the propeller is going to be out of balance. You're going to be pretty unhappy about it, so you're not going to want to fly through icing conditions that day. Now, you got to understand that these propellers and the heating elements on them are designed to be flying through really cold air, with these propellers spinning around near redline RPM and flying through the air really fast. And in fact, of course, the air going through the propeller is faster than the forward speed of the airplane. So it's going to pull a lot of heat energy off of these de-icing boots. So they're going to have to generate a large amount of heat. If you're on the ground, even with the propeller spinning at idle, there's not nearly as much airflow across the propeller, and it's probably not nearly as cold. So it's very possible, or of course if you're doing this pre-flight check when the propellers aren't even spinning before you start the engines, it's going to be possible, in fact likely, that you're going to overheat. The wires are going to get too hot, the rubber boots are going to melt. So when you're doing the test on the ground, you need to make sure that you follow any restrictions. It'll say don't operate it for more than 2 minutes, or don't operate it for more than one cycle. There's going to be some restriction, so you only operate it for a short period of time when you're on the ground, so you don't damage it. And of course, I already told you, you can run it, although it's called a de-icer, it'll de-ice and it anti-ices both very well. Here's a picture. You can see the rubber boot right here. It's nice and smooth on a propeller that's an alcohol prop. You'd see ridges right here for the alcohol to help get spread out towards the tip. On hot props, the rubber boot is smooth, and I've got a closer one you can see. Here's the propeller spinner. Here's the back plate of the propeller spinner. I'm going to zoom in here on the next shot. And you can see there's 3 rings here. One's going to be ground, one's going to be hot for the inside, and one's going to be hot for the inboard and outboard heating elements. And here's a block. There's only one. This one's busted, but there ought to be 3 carbon blocks or brushes on here, so you would be able to check this during pre-flight as well as looking at the boot for condition. Here's another picture of airplane propeller that's got hot props. You can see there's 3 connections here. One is ground and one is positive for one heating element and positive for the other heating element. Rain control systems on little airplanes like a 172 or a Seminole, you keep it clean, you keep it waxed, and the slipstream doing 100 miles an hour, 60 miles an hour, whatever, ought to blow enough of the rain away. We don't use windshield wipers on airplanes with plexiglass windows because even wet, the windshield wiper would scrape and scratch up the plexiglass. On bigger aircraft that have glass windshields, if they have glass windshields, now you can have windshield wipers. Of course, you never operate the windshield wipers unless it's wet. The windshield wipers are typically powered by electricity or by hydraulics. A former professor here at Embry-Riddle flew 727s, and he told me about the chemical rain repellent. It squirted rain repellent fluid at the bottom of the windshield, and the relative wind would blow the fluid up the windshield and reduce visibility. So he said once you used it once, you never used it again. It was terrible. Bleed air, however, works really quite well. In fact, I'll show you a picture here. Here's a small Cessna jet. You can see in front of the windshield here is a vent. It's about 1/2 inch thick and 1 foot or 1.5 feet wide, and it takes bleed air off of the compressor of the turbine engine and blows it across the windshield. This works great for getting the rain off, for keeping it anti-iced. However, you got to watch out if you have a plexiglass windshield and you're doing this. I'm sure there will be a restriction for operating this on the ground. This system works well as an anti-icer to keep the ice from forming, and it'll de-ice because it's hot enough. Of course, as you're flying along, the air is nice and cold, and so you won't have to worry in flight about melting your plexiglass windshield. Whoops. Ice detection systems. There are ice detection systems that'll have a light and a warning, a horn maybe, or a message from the computer saying, hey, your airplane's icing up. Some of them will be set up so it automatically turns on things such as pitot heat and static heat. Other systems you'll have to turn them on. Other airplanes you'll have to turn them on manually, so you want to make sure you read the approved flight manual. Remember, ice forms first on things with smaller radii. So if you look out the window and you see antenna that have ice on it, anything that's going to be your first indication of icing. Remember that the tail surfaces, the vertical and horizontal stabilizers, have a smaller radius than the main wing. So if you see ice on the wings, you've got more ice on the horizontal and vertical stabilizers. Now, the reason that this is a significant issue that I'm bringing up again is, let's just say you've got a little bit of ice on the wings. Excuse me. So I'll draw a really deluxe airplane here, and here's our tail surface, and here's our main wing. And if we have icing on the tail here, it's going to disrupt our airflow. And the effectiveness of the elevator as it goes up and down is going to be less. But as soon as we put flaps in, now it's going to make the airflow messed up even more. It's going to increase the turbulence across the tail, and it's going to reduce the effectiveness of the elevator. So if we're coming into land and we suspect icing on the tail, then use less flaps. In fact, I recommend that you try to use no more than half of what you normally would. Now, granted, you'll have to fly a little faster on your approach, and you'll touch down faster, and you'll use more runway, but there are multiple cases of airplanes coming into land, and on approach, as they went to full flaps, they lost control of the airplane in pitch because the effectiveness of their elevator was so little that they couldn't maintain pitch control. So I encourage you, If you even suspect that there's tailplane icing, that there's icing on the horizontal stabilizer, then use less than normal flaps. Don't go beyond half of the flaps that you normally would. You'll be a lot happier that way. Now, if you're going to fly an airplane that's called certified for flight into known icing, it's going to have 5 different things. First of all, one, you're going to have heated pitot and static ports. Heated pitot and static ports. And of course, if you're in icing conditions, you're going to turn those on. Second thing you're going to need is ice. Well, instead of trying to say anti or D, I'm just going to say ice protection. Ice protection. You're going to need ice protection systems for the airfoils. That is for the wings and the horizontal and vertical stabilizers. We're going to call the vertical stabilizer an airfoil. So you're going to need an ice protection system, de-icing or anti-icing, for all of the airfoils on the airplane. Number 3, you're going to need ice protection for the jet engine inlet and or propellers. If you got a turboprop, you're going to need protection for the inlet and for the propeller. So we're going to say and or. So number 3 is you need ice protection for the jet engine inlet and or any propeller on board the airplane. So if you're flying a piston-powered airplane, you're definitely going to need ice protection for the propellers. Let's see. Number 4, you're going to need dual, that is at least 2 separate pitot-static systems. 2 separate pitot-static systems. In fact, I've seen transport category jets with 3 separate pitot-static systems. So for instance, you're flying along in your Cessna 421. It's a big 8-passenger turbocharged pressurized Cessna, and one of your pitot heat systems fails, then you still have a separate pitot-static system to give you good airspeed indication. So number 4 is dual or at least 2 separate pitot-static systems. And then the number 5 thing is you need an ice protection system for the pilot's windshield. You need pilot windshield ice protection. So that way you can make sure that if you happen to fly through icing conditions, you'll still be able to see out the window, not in flight, not during cruise, but certainly when you come into land, it would be really nice to be able to see the runway prior to touchdown. Now, let's say you're flying that 1955 Beechcraft Baron from Flagstaff to Albuquerque, New Mexico, flying bank checks. If that airplane has these 5 things on it, you got pneumatic boots, you got alcohol props, you got alcohol windshield, you got dual pitot-static systems, then they're all heated. If you get into icing conditions, you're probably going to need to advance the power lever to full throttle, and you're going to operate all of your ice protection systems. But the most important thing you're going to do if you're in a piston-powered airplane is you're going to, as soon as you get into icing conditions, as soon as possible, you're going to leave the icing conditions. Turn around, descend, get out of the icing conditions. Yes, you're going to operate all of your anti-icing, de-icing equipment, but you're going to get out of the icing conditions as soon as you can. You need to understand, even if you're in a big piston-powered, turbocharged airplane, say it's that Cessna 421 or a big Piper Chieftain with piston-powered airplanes, and they're turbocharged, and you're up there at 24,000 feet, you are not an overpowered airplane anymore at flight level 240 at 24,000 feet, even in a big Cessna piston twin or a big Piper piston twin. If you get into icing conditions, ice is going to form on the airplane and it's going to weigh more. The ice is going to form on the airplane and you're going to have more drag. You're going to get some icing even on the airfoils and the propellers. You're going to have more drag. It's going to mess you up. You will probably not be able to maintain altitude in known icing conditions, especially if it's really bad. And I'm getting this information from a NASA aircraft icing expert. He gave a seminar here on campus 5 or 6 years ago, and this was the most important thing he said that day, was that piston-powered airplanes, even if they're turbocharged, are not as overpowered as turbine-powered airplanes are, so the margin of how much extra power you've got is essentially zero. You've got to get out of the icing conditions as soon as possible. So if you get into known icing, use all your ice protection systems, but most importantly, leave the icing conditions. Get out of the icing conditions as soon as possible. Now, this last question, what's the most important thing about ice protection? Well, it's not that I want to say don't read the approved flight manual, because that's certainly important. You're going to need to know how to operate everything. But I submit, and of course I'm grading the test, that even more important than reading the approved flight manual is talking to a pilot who has flown that make and model of airplane before in actual icing conditions, and say, hey, how thick does that ice need to get on the wing before I turn on the pneumatic boots? Hey, does that pedostatic heat really work well if it's really heavy icing? Hey, how's that alcohol prop thing work out pretty good? Does it really keep the ice off of the propellers, or does it not work that great? Am I going to be unhappy about it? So my best thought to you is the most important thing you can get out of this section on ice protection systems is that the most important thing you can do, I think that was redundant, the most important thing you can do is to talk to someone who's operated that make and model of airplane, if possible, that particular airplane, in actual icing conditions, and have them tell you how well it worked and any tips and techniques that they recommend. And that's the end of ice and rain control. If you have questions, please send me an email or ask me in class. Make sure you answer all of the practice questions and be prepared to do that, to answer all the questions for the test.